All right, in problem 3, you're given a picture, and this is essentially going to be a ranking task. You got 4 different systems here. The first one, which is A, says you've got a pendulum of length L, and the mass attached to it is M. So it's going to be very conceptual here. The second option here, B, it's got the same length L, but we've attached a larger mass to it. And then C, you've got L over 2, half the length, but twice the mass relative to the first one. And then in D, you have L over 2 again, half the length, but only, or the same mass as in reference to the first one. So there's your 4 options there. And what you're asked to do is you're asked to rank the period of these 4 systems from smallest to largest. So one of the options you have, since some people don't like working variables, is you can put in numerical values. You just got to say it consistent with the problem here. If you make L1 and L1, then this has to be 0.5 and this has to be 0.5 because it's L over 2. Let's say you made this 40 grams or 0.04 kilograms. That would have to be exactly twice as much, or 0.08 kilograms. So you got to be consistent if you want to make up numbers to plug in here. But we actually don't need to do that if we understand our relationship very clearly here. And the relationship is this. G is set in stone. We're on planet Earth. If we went to another planet, that could matter. But here, they all have the same value of G. What matters is the length. So if I'm looking here, this has the same length, this has the same length, and this has half the length. Then what you're going to see is that these are smaller values of length. Those are going to give us smaller periods. These are larger values of length. These are going to give us larger periods. And the other thing is the M's, the masses, they don't matter here. There's nothing in here that deals with the mass. This process is independent of mass. So essentially, C and D are my smallest ones, and they're going to be equal because they're the same length. A and B are also going to be equal because they have the same length, and C and D must be smaller than A and B. So that's how I rank those systems. The next one, actually, let's go to the frequency. Frequency is 1 over the period. So basically, larger values of T are going to give you smaller values of F, and smaller values of T are going to give you larger values of F. So it's going to be reversed here. If you have a short period, you have a high frequency, and if you have a long period, you have a low frequency. So second part of the problem is rank the frequency. Frequencies would be A and B are equal. They're still equal because they're still the same period, but their frequency would be less than C and D. So it's like the exact opposite of the answer that we're looking at in terms of problem A when compared to problem B. If we look at the spring setups in problem 4, you're given values of K, how far they're stretched, and then they're let go, and then also masses attached to it. So if I'm looking at choice A, the K value is 5 newtons per meter. The mass is 1 kilogram, and the stretch value, we'll call it X, is 0.4 meters. For B, we've got a K value, same K value, 5 newtons per meter. But the mass is different here. The mass is 2 kilograms. And then we're stretching it 0.2. X equals 0.2. C, K is less. It's 4 newtons per meter. The stretch is 0.2, and the mass is 5. And then on D, it's the last one, we have the K value being 1 newton per meter. The mass attached to it's 1 kilogram, and then the X value is 0.5. If we want to rank the period here, the relationship is 2 pi mass over the K value, square root. And at no point, and we've seen this before in the demos in the lab that we've done, does this factor in. We don't care about the amount of extension that occurred here. That doesn't matter here. What matters is M and K. And essentially, we learned that a large value of M yields a larger period, And what you should also see here is that it's the opposite for k, since it's in the denominator. A larger value of k would give you a smaller period, and a smaller value of k would give you a larger period. Now, because we have numbers, it might be easier for us to just evaluate the numbers, but you do actually see some things consistent here. You know, like if I were comparing this one, they're the same value of k, but this one has a larger mass. So right away, I know that B has a larger period than A. But why don't we just evaluate it, because that would make life a lot easier in terms of trying to compare them, since we have several floating variables here. So if I do 2 pi 1 over 5 square root, that's going to get me an answer here, and I get a period of 2.8 seconds. This one has a mass of 2, so I'll put in those same numbers except 2, and I get 3.97 seconds. So right away we see that this has a larger period than this. We've got a k value of 4 and a mass of 5, so it's going to be 5 over 4 in that square root, and we're going to get 7.02 seconds there. You may notice the k value went down and the m value went up, so both of those will yield larger periods. And then the last one, it's just going to be 2 pi times 1 over 1, and then square root that. So we'll get 6.28 seconds there. So rather than trying to like look at things and compare them, it's just easier to evaluate numbers in this case, unlike the previous problem that we saw. So just trying to go from lowest to highest, now it's pretty easy because we got the numbers right in front of us. A is the lowest, right, out of all these that I'm looking at. And then what we have is that that's less than B, that's less than D, and D is less than C. So that would be the order that I go in for these springs here. And that is for the first problem, the period. As we said before, period and frequency are inversely related. So if we're ranking frequency from lowest to highest, it's going to be C is less than D is less than B is less than A. And if you wanted to, you could calculate the frequency value for this, 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 and this, just using the formula that frequency equals 1 over period, and you're going to confirm that mathematically if you want to prove that to yourself. So it ends up being, I would say, pretty straightforward questions, not that difficult to work through. The numbers are very digestible here. We're not doing any complex math, so that's a plus. Hopefully going through these problems will make it so that, you know, whatever assessment you take on this on Friday ends up being very manageable for you.